Alright, so we've discussed how to compute directional derivatives a little bit more easily than the limit definition. Now we're going to introduce another theorem that actually discusses a few nice properties about the directional derivative, and thus is very, very important. Okay, the big theorem, that theorem 6.2 or whatever, right? It gave us a dot product, right? Well, kind of a follow-up that I have is how large or small can the directional derivative be, right? So if I think about the directional derivative in that direction of the unit vector v of, or at a, okay, we said that that was the gradient of f at a dotted with v, right? But the dot product, right? I know that, well, that's actually can be defined as the magnitude of the gradient times the magnitude of v times the cosine of the included angle. Well, I also know that cosine, right? Cosine is between 1 and -1, right, as a value. So can't I say that then this implies that the directional derivative in the direction of v is between minus the gradient, and I'll also mention that this is 1, right? Okay, by the definition of a unit vector. So really the directional derivative as a value is between the negative gradient of f at a and the positive magnitude of the gradient of f at a. Okay? So that's kind of the premise with which we explore the Mega Theorem, which has all these different components of the properties of the directional derivative in there. Okay, so magnitude of the unit vector, and I'll just, it is bolded, but it doesn't look like it. So the magnitude of the unit vector is 1, right? And we have to assume that that f is differentiable, just as we did in the big theorem. Okay, and then as a result, we have that the directional derivative in the v direction at a is equal to the gradient of f at a dotted with v. All right, and then we get 4 kind of nice properties. Okay, the first is that it's exactly what we saw above. So the directional derivative is between the negative gradient, or the length of the gradient at a, and let me just get my notation down, and the positive gradient at a. That's the first thing. Okay. Second thing, okay, is that there's a maximum value of dv at a is that length of the gradient at a. Okay, and then that corresponds to when theta is 0, right? And so if we think about the geometry, that means that v is parallel to the gradient of f at a. Okay. And I just realized something I want to fix. This should be dvf of a, so please make that correction. Okay. And then as a result, the third thing is, if you think about this, right, if the maximum value of the directional derivative is the length of the gradient, really we're saying that the gradient of f at a points, and I'll make this a clearer symbol, gradient of f at a points in the direction of maximal increase. Okay. And then also a fourth thing is that if we have theta is pi over 2, right? So then what this is going to imply is that our unit vector is perpendicular to our gradient f at a, then dv, so the directional derivative in the v direction is naturally going to be 0. Okay, per the dot product. Okay. I will also say one thing is that here in 2 and 3, right, we talked about maximum values. We can also define similar things for minimum. Okay. Similar for min. The only thing is that we're going to have a minimum at theta is pi. Okay, and so that's the Mega Theorem that we're going to use, and we're going to see it visually in the next set of video, or in the next video. But before, I do want to go on to a quick example. Okay, this is I just stole this from your textbook number 15, and so we're given an inchworm crawling along graph paper. Intensity of a magnetic field is given by that equation. If Igor, the inchworm, is at that point, we want to figure out the curve which he should travel to reduce the field intensity as rapidly as possible. And then also just a follow-up question is, how fast does the intensity decrease? That second question is not in the prompt, but I added it. All right, so per what we just saw in the Mega Theorem, right? The Mega Theorem said, well, if I want to determine the direction that would increase or decrease as rapidly as possible, I need to look at the gradient. Okay, so the gradient of m, and I can find that to be 6x and 2y. Okay, so that would be the direction. That's not necessarily the curve, right? And I could also evaluate this to be at a certain point. So at 8, 6, this would be 48 and 12. Okay, but so we'll get back to that in a moment, but it's to describe the curve along which he should travel, right? So this is the direction. But what this is meaning is that the derivative, if you will, so it could be, I'm saying y is equal to m. I'm being a little sloppy with my notation. dy dx, this is saying that the instantaneous rate of change is 2y over 6x, right? Okay, just using those as partial derivatives, which then I can simplify to y over 3x, and oh look, we have a differential equation that is separable. Okay, so I'll give you a push in the right direction, and then I'm going to jump. Okay, so we would separate dy over y is equal to 1/3 dx over x, and then we would integrate, right? Okay, and dot dot dot, do a lot of things. You end up with y cubed is equal to cx, and using the initial condition of that point, you would end up with y cubed is equal to 27x. Okay, and that would be your curve. Okay, as for the question about how fast does the intensity decrease, we would say at that point or whatever, and that would just be, that's where if we look at the gradient, the value of the gradient at that point, we would say that that the magnitude of the gradient at 8.6 would be the rate of change in the intensity. And so if you compute the length, this is approximately 49.5. Okay, you can verify it with a calculator. Okay. I should actually also say one more thing. Technically, when I did this, I should have had if he wishes to reduce the field intensity, right? Technically, I should have had negatives here because it would have been in the direction of opposite of the gradient for maximal decrease. So technically minus 6y minus 2y, but they ended up washing out algebraically when I was finding my curve. Okay, so Mega Theorem 101. Remember those properties, and we're going to see those properties visualized in the next video.